It's me. Draft Science video. Yeah, we're going to talk a little bit more about the two slit stuff. I mean, I have made some progress with the paper, so I'll leave a link below to that once again. But it does get a little tricky because, this explanation of why there's a difference between single slit and double slit is pretty good. I mean, solid. This gets into a little bit of trouble because people can just claim that this is a quantum effect and blah 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 blah, and so I have to come up with a more rationale to explain why not only is that unnecessary, but that it's wrong. And I've been working on the math too, which is a little complicated. So anyway, I just figured I'll start the papers on the other subjects, just because I don't think I'm going to be able to finish this two-slit one until I work out some of this stuff. So anyways, but going through the math, I've always been sort of unhappy, with this argument that the math does all these things and it doesn't really do much at all, and the assumptions built into it are kind of dangerous. So I'm going to play this Khanacademy of medicine, doing the two-slit, which is kind of weird. I don't know what medicine exactly has to do with two-slit experiment, but anyway, I mean the single slit, and the contrivance of the whole Huygens bullshit and how these are all just gimmicks. And one of the gimmicks in this is one form of the equation I've seen. So this is the distance of the impediment, the thing in the middle, and then the sine theta is the angle that the slit is producing, technically. The m here would be just the number of the slit, which one it is, which one of the fringe is, times again the wavelength. Nowhere in this equation is anything to do with the light source or the distance to the target or the distance of the opening. And I'm supposed to believe this math has something to do with something. I mean, so obviously those are assumptions. There's somehow an assumption built into this math that basically assumes that the slit is the width of a wavelength. That's the only way they could possibly be doing this math without it. This sine theta is essentially establishes that. I guess that's what I should say. This essentially equals, is defined by the wavelength of the the opening, the distance, the width of the opening, will dictate how many degrees of that will create the angle of their triangle, the sine theta. The angle of the triangle will be dictated by the length of the slit. So if they just gave you the length of the slit, you wouldn't need the sine theta thing, because that's automatic. So that's sort of like a trick here, is that it's hidden in here. But still, a presumption inside of that even is the fact that because it's not directly accounted for, like it's not distance. So essentially this is saying distance times some percentage of the wavelength, which is what you're left over with, once you do the sine of the angle. You do the sine of the angle, you'll end up with some point number, some percentage of 1. So you're just multiplying the distance of the impediment in the two-slit experiment times some percentage of 1. And then when they do the single slit experiment, they just divide it all by 2, which is sort of a convenience. but the trick is because they didn't put the total distance in, the distance from the total both wavelength, both open slits plus the center impediment. And so when they move to the math for the single slit, it's really what they've really done is made the slits wider. So technically, because they aren't identifying the slits in the math, in the width of them, so that when they change the distance, because they've now changed the distance, the center impediment is now 0, and they're going to replace the center. They're going to replace the d term with the distance of a half a wavelength. So instead of d being the actual distance of an impediment, they change it to d equals 1/2 of one wavelength. And that's just such an overt cheat. Anyway, I probably lost the. I mean, this is going to probably get, this video will probably not be terribly interesting to people who don't know this stuff, and then the people who do know this stuff are probably going to be saying, well, Gary, you said that wrong, you did this with you, but whatever. I'm just saying this is the stuff I'm playing with, in the sense I have to deal with the math somewhere in here, so I'm going to try to deal with it. But of course I'm going to argue that the math is contrived, that all I really have to do is just take the inputs and the outputs, and then I'll just change the variables to the variables I think are important, which is the width of the slit and the distance to the target. And by doing that, I can create math that just based on a regular, it's all a percentage. I mean, it's a known, the factor that you multiply the wavelength by to figure out the diffraction angle is consistent. Each color light will be proportionately different. So no matter what nanometer number I put in, the proportion of the angle to the wavelength will be the same. That's why they're just going to be spaced wider. I think I said that correctly.
Let's talk about single slit interference. Now, if I were you, I'd already be upset and a little mad. Single slit interference. Wave interference, is by definition multiple waves overlapping at a single point. So how could a single slit ever produce multiple waves that could overlap? I mean, when we had a double slit, if I put a barrier in here and we have a double slit, at least then, okay, I send in my wave, it gets over to here, there's a small hole. We know what waves do at a small hole. They diffract, which is to say they spread out. At least with a double slit.
So again, this is one of those things where first, now everything's done with these more straight waves, the laser beam. But besides that, I mean, they never talk about really what happens with water waves. And I guess I would argue that water waves bend because of friction. They bend because the water rubs against the surfaces and it's slowed down. And so the water bends because the water in the center isn't slowed down. The water on the slit sides is slowed down, and that's what creates the waves. Now, there's no parallel for this in this wave theory of light. There's no explaining exactly how the light does get bent into this wave front now that's not straight anymore. So in water waves you have a mechanism, a physical mechanism, and in their light examples, what's the physical mechanism? How does the straight line of the laser beam get bent?
You would have two waves spreading out. Now they can overlap. Interference. But for a single slit, how are we ever going to get this? Well, I never really told you what.
And again, if you reduce it to a single photon, the argument is the single photon is a wavefront. Now, is the argument that the wavefront of a single photon is a bent wave automatically? So it's already a rounded wave, and so then it automatically has to somehow retain that roundedness? I mean, how exactly when it goes through this slit that's supposed to be a wavelength or less wide, why does it bend even more eccentrically? Because it's a more eccentric bend to be able to create the interference pattern at the distance.
Why do the waves spread out at a hole? Why does diffraction happen at all? Why, when waves encounter a hole?
Right, see, so now he said diffraction, right? Why would diffraction happen? But that's not what you're arguing happens, right? You're arguing that it's a wave here and it's a wave here. That just makes sense. It's always a wave. So it's not about diffraction, it's about interference. So, it's all this mixture of terms. And this is another part of this whole thing that just gets kind of lost, is that they keep the two concepts are now the same. And, that's just kind of unfair to the argument, isn't it? I mean, a photon being diffracted just has to do with it going through a lens or something. It going through something, some mechanism, some physical mechanism that changes its course because it interacts with an electron, and through that interaction, the electron goes this way and it goes that way. They exchange direction.
Do they spread out? And the answer to this question is the key to single slit interference. And the answer to why they spread out at a hole is something called Huygens principle. and I can't say it. This is a Dutch physicist, scientist who figured this out. Huygens principle, and I apologize right now to all the Dutch people out there. I'm butchering this name. Huygens principle, easier to spell than to say. What he said, he figured out something ingenious. He figured
Right. You know, this is a gimmick, right? So an ingenious gimmick. So okay, I'll let him do it, and then I'll point. You know, it's just so obvious.
Figured out this. If you've got a wave coming in, these wave fronts. Remember, these wave fronts are like peaks, and in between them are the troughs or the valleys. If you've got a wave front coming in, propagating this way, you could say, yeah, that wave front moves from here to there. That's what it does. Or he realized with a wave, you could treat every point on this wave as a source of another wave that spreads out spherically, if in the forwards direction. This wave spreads out spherically, this point here. He said that a wave front you can think of as an infinite source of waves. Each point.
Right, so that's basically turning the photon back into a photon, right? It's just basically saying that each photon has a trajectory, even with that wave direction. And so you're just giving the photon back its directionality, which is supposed to be it's not supposed to be having. So, I mean, it's sort of a cheat. And then beyond that is obviously the proportion of these waves, these little mini waves in here would be reduced completely proportional to this wave. So obviously when you get to the halfway point, you know, they would be, what's the right word, they would be destructively interfering, and then they would be maximally constructively interfering at this point. So you just create the same. It's just completely built out of something you contrived, and so it's mathematically completely proportional. So you're finding it's just a way of cheating to just say, let's just pretend that the wave interfered with itself. So you're just really just cheating and saying this is an artificial way where it's harmless to the math, because these waves will end up doing exactly what these waves are doing, because they're proportionally the same exact, you know, I'm just saying if this is 10 scale, there's 10 of them will reach here, you know what I mean? 5 of them would reach here. It's completely proportional. So you've just miniaturized it and done it inside your thing, and then you're saying that's what caused the thing. So you're just creating a reverse fractal or something. It's just a huge cheat.
Point is the source of another wave, and you're thinking, this is horribly complicated. What kind of mess is this going to give you? Well, if you add this up, these are going to interfere with each other, constructive, destructive, in a way that just gives you this same wave front right back. This is crazy, but true. If you let every point on this wave be another wave source, it will just add up to another wave front here. You'll just get the same thing back. And this is the key to understanding why diffraction happens.
Right, but is that the mechanism of how it happens? So again, you made up a synthetic piece of math to create your artificial. So now you'll have the opportunity in the single slit to create 2 waves, and you're going to completely artificially select 2 waves at a specific distance. And so even though there's a million waves, you're just going to select 2 of them and pretend those 2 are the only 2 that do anything. And so how does this math in any way represent the reality you just Huygensed? It doesn't. So it's just cheating.
Is because the wave was already diffracting, so to speak. It was already doing diffraction. Every point on here was doing diffraction. It's just it always added up with the other waves around it at every other point and gave you the same wave back. But when there's a barrier...
Yeah, so it's almost the same thing as saying that photons, that say if they say red light, is made up of ultra red light. You know, there's a bunch of little frequencies inside of the red light frequency, you know, and they're all proportional. They're exactly miniaturized to whatever light they're part of. So it's an ultraviolet light, you know, with a narrower frequency. Then the little sub particles all have the same littler distance. And if it's infrared and it's bigger, then all the little sub particles have a little bigger distance. So they're just making up a fake world inside of it to say it's like me creating a little man inside my brain, saying he's controlling my brain, without explaining how he got a brain. This is just whatever they call that, infinite regression bullshit.
When there's something in the way, these here can't rejoin up with their buddies. You just get this one here spreading out, and then this one down here spreading
Yeah, right. So there's an infinite number of them, and now he just turned them into two, right? So there was an infinite number. We certainly threw, you know, a slit that is, you know, almost a millimeter wide, you know, or even a half millimeter wide. Plenty of room for lots of photons to go through there. We know that. So, you know, here we had an infinite source, and all of a sudden now the source has been cut to two, conveniently.
spreads out. All the rest of these get blocked. Now that these are blocked, they're not going to get to interfere constructively and destructively with these points here.
Right. So is he just I mean, can you cheat more overtly? Like I said, this should really be a bunch of little waves here, so you should have a ton of interference by the time you get here. All these micro infinite. He said the word infinite number. Well, where's the infinite number? Why didn't any of the rest of the infinite number go through the slits? How did you control? How did you stop them? What were they blocked by?
And so what do you see when it hits the hole? You just see this thing spreading out. So it was always diffracting, so to speak. We just didn't notice it because it always added up. When you've got a hole or a barrier, that's when we actually notice it. And this is the key to single slit interference, because if I get rid of all of that, if we imagine our wave coming in here like this, well, this wave's going to hit here. Every point's the source of another wave, so this point's going to start spreading out, this point's going to start spreading out. When we have a single slit, we really have infinitely many sources of waves here.
Right. So just a minute ago, though, you drew it as one in the two-slit experiment conveniently. So again, this is the same size slit as in the two slits. So you have to remember this: the single slit experiment isn't a slit twice as big as the two slit. It's the same size as one of the slits in the two slit experiment.
And since some of them are blocked, we could see an interference pattern over here on the wall, because these can interact and interfere with each other. What interference pattern are we going to see? Well, on the wall.
Right. If it was an infinite number, we would see a whole bunch of interference patterns here, because there'd be a whole bunch of interference lines. But what do we see? Yeah, we just see, you know, a very pale interference pattern.
All over here, we see a big old bright spot right in the middle. And if I were guessing, I would have thought that was it. Big old bright spot because you shine a light through a small hole.
Right. Now, if you use a laser, this isn't true.
Single hole, you'll get a big bright spot there. The weird thing is, this jumps back up, goes to a minimum, a 0 point, and then it jumps back up, and then it comes back up again, and you get this. These are going to be not very pronounced. These aren't very pronounced. You get a big bright spot in the middle.
Right. See, that's only true in the old days when they had an aperture here. Okay, so the aperture made sure the light was bent coming in. All right. With the laser beam, the light's not bent. It's coming in straight lines. And so this pattern with a laser beam, this is a lot more. This interference pattern is a lot stronger than this indicates, because this math was done with an aperture that bent this wave, quote unquote. That this light was the old way with an aperture. The light here is much more intense than the light here. So obviously you get a huge peak here because the light coming in the center where there's no obstacle is completely unobstructed, and that's why you get a huge maxima in the center. But that's, again, only with light that comes in that's not coherent, or whatever the word is, colonnaded.
Relatively weak compared to other interference patterns that we've looked at. And down here jumps up a little bit again over and over here.
Right, so this is mathematically correct for non-laser light, but it's not correct for laser light.
So this is the pattern you see. How can we get this? How do we analyze it? That's what we're going to try to figure out. To figure that out, okay, well, this is I said there's infinitely many sources here with when this wave gets to here. That would take a long time to draw. I'm going to draw 8. So let's say there's 1, 2, 8 sources. Let's just imagine there's 8 here to make this a little bit easier to think about.
it won't matter because he's going to get rid of a whole bunch of that 8.
And the weird part is that this jumps back up here. So let's look at this minimum right here. Let's look at this point where it goes to 0, this destructive point. So the wave from this topmost point, this wave from the topmost, uppermost point has to travel a certain distance to get there. I'm going to also look at the 5th one down, this one that's basically halfway. How about these two? If these two interfere destructively, the argument I'm going to make is if these two interfere destructively, all the rest of them are going to have to interfere destructively.
He just means all the rest of these pairs, but so this is just where they did the half thing. So now they've basically changed the math, and this is going to represent the D component. So where this D was the size of the middle impediment, which establishes the size of the slit, which is going to be a wavelength. So this basically, the math, the thing that was built into the math wasn't the fact that the slits are a wavelength long. The thing built into the math is that the entire slit thing was 2 wavelengths wide, and that the distance thing, the size of the impediment, how to say that, was see the middle impediment doesn't do much in this experiment. I mean, the thing to understand, I guess, well, the thing I'll just write down real quick is just to see, is that what happens is the size of the slit is everything in terms of the pattern you get. So with the slit very wide, you know, where you still get something you can see, the pattern is tight and there's a ton of interference. I mean, it's really tight and there's a lot of it. And it's when you make it narrower that now you're only going to see little bits of it. So, you know, it's non-intuitive. It's really tight with a big wide opening. It's really wide with a little tiny opening. And, you know, that's always sort of something that blocks you from understanding the relationship, is it's almost a backward relationship, and you got to keep thinking of that in the math. There's that inverse relationship.
Why? Well, we know how to play this game. Let's draw our right angle line here. There we go.
So now they're just contriving an excuse, do the same kind of Pythagorean nonsense, do their little angle theta crap, when all they really had to do was say, well, what's half the width of a wavelength, because this is supposed to be a wavelength wide, what's 1/2 of that? And we'll call that the distance, as if we made, so what they're really doing to the circumstance, to create this wider pattern, essentially, they're widening the slit by doing the math to fit a wider opening. So they're taking what would have been this total in the 2-slit experiment, so that the total of the opening plus the impediment plus the opening, and they're now representing that as any change you make to this. So they've now cut that in half. You know, that's what this represents in the math. This is now D. Even though it's a half the measurement of a wavelength of the slit, they've changed it into D. And so now they've changed the size of D, where in the 2-slit experiment D was a wavelength. Now it's only a half wavelength. But they've kept this same difference. Okay, so this was built into the equation, is the assumption of this distance. So now essentially the slits have gotten wider because they've made D smaller. So by making D smaller, they didn't bring both of these in. They made this opening bigger. So this got bigger. And that's the difference. So as you make the slits wider, then you're going to create more of that. No, it's exactly the opposite. but anyway, yeah, because there's no slits, obviously. So the single slit is wider. Still saying that wrong. Well, anyway, let's play the video, and then I'll get to it. I'll find my opportunity. But you can see it coming. I mean, I'm just saying this is now D, which before it was a measurement of the width of the impediment. Now it's a measurement of half of the opening.
Yep. And so we know that, okay, if these are going to interfere destructively, this is the extra path length this extra path length that this second wave, this lower middle wave, has to travel has to be what? If I want destructive over here, it's got to be a half wavelength, 3/2 wavelength, 5/2 wavelength. That's how much it's got to be in order to be destructive. So if this is the first point, let's just say that's 1/2 of a wavelength. And what's the relationship between the angle that this is at on the wall compared to the center line? Well, we already figured that out, remember?
See, and there's so many assumptions in here. These are really parallel lines, but they break them into this, just because they can cheat. Because obviously the distance thing, this projection is so far away that for the purposes of reason, these are really parallel lines. But obviously when you draw it in this scale where this is pushed in, this has to be a way across the room for this to be a fair drawing. So, that's where this, well, anyway, it doesn't matter. But anyway, let's play along.
That relationship was d sine theta equals the path length difference between these. That we derived. The screen had to be very far away.
So instead of using the path length distance is really just another way of, because like I said, it's automatic what this angle is going to be if you know this. So if you know the width, you already know this angle, because it's always going to be the same. The light is always going to bend at the rules of diffraction at the reflective angle. So those rules are established.
Way compared to the width of the hole.
And the percentage difference between blue light and red light is always going to be the same percentage difference.
But that relationship still applies. What would D be in this case? Now we have to be pretty careful. We have to be careful because this hole has a certain width. We'll call that width W. So if this hole has a certain width W, how far apart are these? These are not W apart. These are W over 2 apart.
Right, so it's just completely arbitrary. I mean, he chose to, you know what I'm saying, he draws 8 dots and he just decides, well, I guess he should have had one in the middle here, so he should have done 9, right? Well, anyway, and then just decides to create his artificial, I'm just going to choose these 2, and they're just happen to be half a wavelength. I mean, this is just contrived. And again, why isn't this width important in the 2-slit calculation? Why are you bothering with this theta crap when you can just replace it with a function of the width? Because as soon as you establish the width, you establish the angle.
And so what's the relationship here for the path length difference between these two? Well, if they're W over 2 apart, I'd have d sine theta as the path length difference. So d would be W over 2 times sine of the angle that this makes to this point on the wall. And if their path length difference is lambda over 2, then that would be destructive. So equals lambda over 2. And this is a little weird already because, look, I can cancel off the 2's. And what do I get? I get that W, the width of the entire width of the slit, times sine of theta equals lambda. This is giving me destructive. Remember before, all the points that...
Right, so all he's saying is this angle, sine theta, is going to be obviously the width times a percentage, a point number, so it's in nanometers. So the width is in the same function as the frequency, and so you're taking the width of the slit, which assumed to be the slit is the same size as the other thing. This sine theta almost has to be 0 then, equals the wavelength. So that doesn't even, that on its face can't possibly work, right? I mean, this width is supposed to be a little bit narrower than the frequency of the light you're putting through it. So, well, yeah, so sine theta would be, this could be a 0.8 or a it'd be this width would have to be bigger than a wavelength, because the point number is going to make this number small, right? I mean, you multiply something times a fraction, you get something, it's less than 1, so you're going to get a number that's smaller than the W. So again, how could this width possibly be as wide as a wavelength, and then you're going to multiply it times a sine, because a sine is always going to be a less than 1. How can that work? Can't work.
Were integer wavelengths were giving me constructive. This time it's giving me a destructive point over here. And the reason is we played this game where W is the whole width. These are only W over 2 apart. That 2 cancels with that 2. Okay, but I haven't really proved that that they should all be destructive yet. This is just for these two. We've got infinitely many more in here. How are we ever going to show that if these two cancel, the rest of them cancel? Well, we'll just pair them off. Look at this. Now imagine you come down 1. I go to this one. I consider this wave that makes it over to here. And the next wave down from this other one here. So I move this one down a smidgen, I move this one
how
down
convenient.
a smidgen, and I imagine these two waves traveling a certain distance to get
Right,
over to...
right. So it's just basically saying no matter what number I contrive, I'll just make wave fronts the proper size for that number. So it's just contriving that this wave technically, you know, at this first point was a wave big enough to be half the... For these two to interfere. So these two are going to interfere with each other. Well, I guess it wouldn't matter how big the wavefront is, because eventually they're going to interfere before they get here. But yeah, that's just bogus.
This point. What relationship holds between these two? I can do the same thing. These are also W over 2 apart. So this here.
So we'll just ignore all the effects of this wave with this wave, or this wave with that wave, or any of these other waves interfering with each other. We just eliminate them from the equation, and we only use the 2 that we want. So we just basically turn the single slit experiment into a double slit experiment, conveniently.
Is also W over 2. So I'd get the same relationship. I'd get W over 2 sine of, is that going to be the same angle? Yeah, it's the same angle, same point on the wall. This is really far away, so these approximations are hold where these lines are supposed to be approximately parallel because this screen or this wall's very far away compared to the width. That equals, well,
they're not approximately parallel, they are parallel, you know, but whatever.
That's going to be the same thing. I got W over 2 times sine of the same angle. Shoot, that's got to equal the same thing that it did up here. If the angle's the same, my W over 2 is the same. That's also going to equal half a wavelength. That's also going to be destructive. These two will also interfere destructively.
So, again, the width has to be this width has to be larger than a wavelength of the light. And so that would tend, the wider you make this, then the tighter this gets. And that's not the effect taking place here. So, yeah, that's wrong.
I can keep playing this game. I can pick this point here.
Well, don't do it.
Here,
I
and
mean,
the next one down. These two would have to be destructive. I can pair them off and keep pairing them off. I get destructive for all of them. I can annihilate all of them by pairing them.
Right, because you contrived the halfway point and said that's the thing that's significant. And so you just arbitrarily decided which ones you're going to call real photons. And that's it. You just made 2 photons go through the slit. You're just picking 2 photons and saying, I'm going to pick these 2 photons and make those 2 interfere with each other. Cheat.
Off and finding a partner that's destructive to that one. And so, this really is a destructive point. This point over here.
Yeah, I guess the simple way to look at this equation, right, is basically saying, look, width is supposed to be the wavelength or less. So just take this wavelength number, put it over here, and then put in parentheses minus some little percentage times sine theta equals wavelength. How can that possibly work? How could that possibly be true? The whole point is that it's supposed to be constricting this light frequency thing. It's supposed to be a little bit smaller than the wavelength, not bigger than the wavelength.
Here, all the light is gone, completely annihilated, gives you destructive. So the short of it is that this relationship here, this relationship that W, this slit width, times sine of theta, the angle.
Well, let me go. I had a page open here. Just yeah. So the smaller the slit, the tighter the pattern. the wider the slit, the looser the pattern gets. That's where you get this kind of crap. So wide slits with two slits give you this kind of blob look, you know, with lines in between it. This is a synthetic thing. This isn't actual, just because they can't make the slit small enough to make it do that. But you can, frankly, with a green laser, you can get a pretty tight pattern. So narrow slit, tighter, wider slit, wider. Well, that's anyway how it works in the single slit. If I make this slit smaller, then it starts looking more like this. Okay, so yeah, see, it's just so hard to keep all this shit straight. So the tighter this slit gets, the more bounce you get in this thing. I'm just trying to see how this drawing would be affected. Well, I can't. This doesn't have any relation to, like I said, this is so out of proportion just because this isn't what happens with lasers.
Same angle we've always been defining it as, equals integer wavelengths. This time, got to be careful though, this time this gives you destructive points, not the constructive points. It was always constructive before. This gives you destructive points now. And you might be upset, you might say, hold on a minute, we only proved this was just for n equals 1, or m equals 1. One wavelength. We didn't prove this for anything besides m equals 1. Well, you can just as easily show that 3 lambda over 2 would also give destructive, or 5 lambda over 2, that would give us all that.
Right, so now this is just saying m is the number of these spacings. So now he's saying this is a wavelength wide, which is totally dependent on this distance, which is nowhere in any of these equations. I mean, it's subtly in this equation in the sense of taking that theta number, I mean, you know, sine of theta is this, in some respects, incorporating this distance. So yeah, you either have to have it as an assumption of the math, the distance, or you have to, or that's probably why they're playing with the sine theta, is because sine theta gives them a way of hiding the fact that this distance has to be in that sine theta. You'll change the angle by changing the distance. So if I just give you the distance ahead of time and tell you how far away the target is, then you don't have to do this sine theta. So the whole thing can be done without doing any of this draw two-liney, you know, Pythagorean crap, if I just give you how wide this is and how far away this is. So I'm just saying they're making it look like interference pattern because they're forcing the math to force you to do these two lines to create your stupid sine theta, because these two lines will tell you how far away the target is. I mean, it's just engineered. It's an engineered formula, and I'm going to keep arguing this is overtly wrong.
Odd integers here. So m here can be, it can't be 0. We'll talk about that in a minute. It could be 1, 2, 3, 4, 5.
Right, or negative 1, 2. So they just go from the center, and this is 1, this is 2, 3, or this is negative 1, negative 2. So it's just another gimmick of the math. These are just arbitrary designations that allow you to say how far are you from the central maximum, essentially. So it's another way of just saying this is really a distance number, and the distance is going to be the wavelength. So these points will be a wavelength difference, which again, I can't see how that could possibly be true without knowing this distance, because it can't be a wavelength distance. I mean, depending on where I put this target, there are going to be all kinds of different distances. Depending how far the way the screen is, the projector has a different size movie. I mean, this can't be right without a huge assumption built into it somewhere. I really can't.
5 and so on. 1 we already showed. 3 you get, well, if you made this 3 halves wavelength, that's also destructive, that'd be 3. 5 halves wavelength, The 2's are always canceling. So 5/2 wavelength would work. What about the even integers? How do we get these? Well, those come from the fact that I didn't have to pair these off with the top one and the middle one. That's dividing this into W over 2. So pairing them off by lengths of W over 2, I can pair them off, I can divide this by any even integer. I can imagine pairing off, instead of doing the topmost one and the middle one, I could do the topmost one and skip one down here. And so I can pair these off. If I divide this into...
Right, then you're dividing it into 3's, and so then it's 1/3. So, yeah, duh, it's still this distance that you're just fucking with, so you're just establishing the distance. So, yeah, obviously the angle changes because of the distance. The further away it is, the smaller the angle gets. Gee, so then you have to divide by a bigger number, a proportional number. But it's all proportional, so it's just another gimmick.
This distance right here, that distance would be what? That'd be W over 4. And so I can imagine pairing off, okay, if these two cancel...
Well, I figured it would be 3, but yeah, I don't... I think this would be W over 4. I think this is W over 3, so I think that was his mistake.
If those 2 points cancel, then the next one down, so this one here, and this one here would also cancel by the same reasoning. And so I can play the same game now, but W over 4 would be how I divide it. I can't divide it by...
Yeah, there's not enough dots here, so that's the problem. So you got 1, 2 would take you here, and then I guess if you count this as a... Let's see, so yeah, I have to count this one twice. But yeah, if I go from this distance to this distance, that's 1. And then if I go this distance to this distance, that's 1. And I'm short 1 dot, so that's the problem. We're just missing a dot.
Anything, I can't divide it by 3, or like 2.5, because I always want to pair these off in 2's. Always 2's, that's my whole plan. That's my whole strategy here, is to cancel these in 2's. And I can do that by dividing this by any even integer. So W over 4 would work. What would that give us? Okay, W over 4 is the distance between these, times sine theta, equals, let's just say it's the first one, half of a wavelength. Well, if I solve this, if I move the 4 over, I get W sine theta equals 2 lambda. So the 2's also give us destructive interference. I could divide by 8.
Right, so that's kind of obvious that the second cancel point would be 2 wavelengths away, so that was just sort of obvious. But again, this whole relationship between the sine of the angle times what is supposed to be the width, which is the wavelength of the light, that still doesn't work, so you're still cheating. The width has to be bigger than the wavelength of the light, and it has to be bigger by a relevant amount to be even bothered with the sine theta thing. I mean, the sine theta is basically supposed to be eradicating that width, technically.
Would give us 4. Once I move it over, I can divide by any even integer. Any integer here is going to give us destructive points on the wall. So this would be m equals 1. This would be m equals 2, and so on upwards. So this relationship right here gives you all the destructive points. How come m equals 0 is not a destructive point? Well, m equals 0 is right in the middle. That's the most constructive point. That's the brightest spot. So m equals 0 is not a destructive.
Yeah, and really, technically, it's not, obviously, I would argue it has nothing to do with anything constructive. It just has to do with there's no friction, there's no wavefront, there's light just goes straight through, so duh, it's brighter there.
Point, but any other integer does give you a destructive point. So this is the formula for the destructive points. W is the entire width of the single slit. Theta is the angle, the way we normally measure angle here. You imagine a center line like that. Imagine a line up to your point on the wall. This angle here would be theta. And m is any integer that's not 0. Lambda is the wavelength of the actual light that you're sending in here. Now, this just gives you the
Right, so I mean, obviously this theta wouldn't exist unless you cheat. No, off the center line theta would exist. But then at M2, let's see, theta would be twice the angle. What happens if it's twice the angle and then you do the sine of it? Yeah, this sine thing is just, I can't figure how that could possibly work, because a 90 degree angle has a sine of 0. And so like a 3 degree angle would have a sine of like 0.9 or something. So if you multiply it by 0.9, you have a chance of this wavelength being, this size being, a little bit bigger. So 0.9 will allow you, so if you multiply this distance times 0.9, you could see how it could turn out to be the wavelength. This, wherever his theory, wherever the place is where you wrote that plane, yeah, right here. Well, this is no, it's right up here. W sine theta equals the wavelength. So I mean, so if this W was a little bit bigger, then you did the sine of a very, very small angle, you would get, a little bit of a cutoff of this that would equal that. So this width has to be bigger than a wavelength of the color light he's using. And so as the angle increases, well, anyway, so yeah, he's not doing intensity with this math, so there's no point. Yeah, anyway. Okay, we might just finish the video.
Destructive points. You might wonder, hey, I'm clever. If the integers are giving us destructive points, then the half integers should give us the constructive points. If W sine theta equals, lambda over 2 or 3 lambda over 2, is this going to give us constructive points? And, not really. So there's some complications here. And if you're interested in why this does not give the constructive points, I'm going to make another video.
Yeah, well, that's only because this maxima is twice the size, but if the maxima was the regular size of the two-slit experiment, then you could get away with that crap. So the two-slit thing don't work on the single slit because this maxima is twice the size, twice the width, 4 times the intensity. So yeah, that sort of just breaks using the same math. And again, why is it twice the size? Is because in the two-slit experiment, the strongest light has 2 surfaces right next to it, and in the single slit, the strongest light in the center has no slits, no surfaces. But anyway, so enough. Anyway, I don't know how constructive this was. It's just something I need to do. In just, going through this, trying to figure out which formula is the real formula. Like I said, you just find all kinds of formulas all over the place, and I thought there was more rigor to this than just make up a new formula for each experiment. And I would argue that I don't see any point in doing these. I mean, I thought the whole point of this kind of obtuse math was to put everything on one side and then everything in another form on the other side and say these two equal each other, and then decide which thing you need to solve for, and you'll have it on one side of the equation, and you can just move it to the other side of the equation, that kind of thing. So I mean, I just think in doing this math that we ought to know what all of the variables are, put all of them in the math, and then decide what variable we're going to decide we don't know all of a sudden and try to solve it. But I'm just saying to not put the distance into the math, and not put the width of the slit into the math, and then to use the same math and then change from the distance, the d, the d representing the width of the impediment, and then in the single slit experiment changing the d to half the distance of the opening. I mean, is that okay with people? I mean, is that the way you're supposed to do math? Is that all of a sudden D means a completely different thing? I mean, shouldn't you use a different letter or something? I mean, it's not the same equation, that's for sure. They're just trying to make it look like it's the same equation, and it's not. Alright, anyway, that's enough. So anyway, I have some work to do, obviously, to get this. The math portion of the paper is going to need some work because I still don't have But I mean, what I'm really want to start arguing is that this whole two slit thing, or single slit thing, what's really happening is when you move the two slits together, you're basically just got to pretend that there's an invisible lens in between here, and that in its natural state, when it's not interacting with any other material, it's relaxed and the light travels unmolested. And as soon as you push two surfaces together, the lenses contract, and really what you're creating are just lensing, and the lensing is what's diffracting the light, pretty much. So it's like those force lines bend, and when the force lines bend, that means the electrons have a different position, and the position of the electrons is going to decide which way the light goes. So now that the electrons went from a position of balance to the mass that was, you know, the atoms that they're tied to, the field lines are tied to the atoms that are projecting them into the empty space, and those field lines, when compressed, create essentially a mirror, because they bend the electrons to a different, they create a prism essentially, and it just depends on how much compression there is, how high the angle of diffraction is, kind of a thing. It's probably best to leave it as a type of prism, so the prism gets narrower and narrower, so you're ending up with a triangle. So when it's relaxed, it's like this, and then when you compress it, the triangle peaks, and so the light is getting diffracted that way, and as it gets narrower and narrower, that angle, as this angle gets narrower, this angle gets wider. But that, yeah, well, I still have to work on that, but that wouldn't necessarily create more lines, so I have to make it create more lines. Yeah, we'll need some work. Alright, until next time. It just gets so confusing. Width, slit width, what's controlling how much light gets through. The other thing I want to do as an experiment, I mean, I can't do it, but I need, a light meter or something. Be interesting to see is if, just how much light if you lose exactly as much light as you should. So if you take this width and you projected light through it, how much total light are you receiving right here? And then put an impediment in, with a strict distance. And so you kind of know how much light should be blocked, and just to see if you get that percentage of light still getting through, or whether some of the light is actually getting refracted into these materials. That would be an interesting conceptually. Is there some losses in these slit experiments? Because that might be another cause to say, well, this isn't about wave interference, this is about surface consumption, kind of a thing. Obstruction. But anyway, enough. Sorry, this is not a terribly useful video, probably, but needed to get it off my brain, so to speak. Till next time.